Good morning, everybody. So these are all the people that didn't jump, right? Some of you saw your score. Some of you have been saying, wait, Mr. Bailey, you made a mistake. That's too high. We'll see how many mistakes I made. I didn't go easy on you per se, but we'll talk more about that on Monday, right? When you get them back, and we'll do the exam autopsy. Those of you who have had me before can tell you a little bit about the autopsy, but you're going to be working and perfecting the errors that you made on the exam. Giving the exam back to me in its perfect form, but you get to have help from like everybody, right? Your books, the internet, all that kind of stuff. So, all right, we were doing voltage, right? And today is the day that we're going to bring the integrals back. This is the only time there's going to be integrals in this entire unit. What about what quiz? The answer to the quiz. I totally forgot. So we all get points? Well, you get to grade yourself anyway. Okay, so we'll pause. Reminding me, thank you for reminding me. I tend to forget things like that because I knew the answer, and so I was satisfied. All right.
Have the same amount of, it would low potential but high electrical potential?
There's a difference between potential and potential energy. Potential energy depends on the sign of the charge. Yeah, right? So, all right, let's do this. At this point, I have 5 minutes of derivation that I'm not going to do for you because it's in the book and it's actually not that interesting. So I'm just going to give you the punchline so that I can move on to other things that are more difficult. What we're going to do is we're going to do the same evolution that we did in chapter 21 and 22, right? Start with, so back then we did forces and electric fields of like a point charge, and then we went to a line, and then we went to a ring, and then we filled the ring in with the disk, and then we did it, right? Just this evolution of geometry, as it were. We're going to do the same thing, only this time we're going to do it with electric potential. And the idea here is, okay, that we've got some charge, right? Q. Some charge sitting right here, and then pick a point, any point somewhere in space. That one, sure, why not? We want to know the potential right there. And again, at the end of today, I'm going to show you how we can use the electric potential to get back to the electric field. And I also hope that you see that the electric potential is easier to calculate than these electric fields. So at that point right there, because of this charge Q, and I know I didn't draw it, but this is a point charge. Okay. The electric potential at a point is KQ over R. Now, what's missing in that statement right there? No vector signs. The voltage, the electric potential, is a number. It's positive or negative. When will it become negative? If the charge is negative, right? So there's no R vector here. There's no R hat. There's no absolute value signs from the book. I'm actually exactly the same as the book here because there isn't really any other way to do it. You just put in the value of the charge. And if it's a negative charge, the negative sign goes in there and you end up with a negative voltage, right? Now, voltage, the way we defined it last time, is that voltage was always a difference between two things. A final minus an initial, because the voltage was equal to the change in potential energy divided by the charge. So what are we comparing to, right? Like that point, near that point charge, that's just one of the points of comparison. Because really it should be a delta V. And you won't see delta V written. Like I didn't write delta V on the potential of a point charge here. In the derivation that I'm skipping, I would have shown you that our other point of comparison is infinity. infinitely far away. By definition, the voltage at infinity is defined to be 0. You can get 0 in other places, like if I've got a positive charge and a negative charge next to each other, where's the voltage going to be 0? If it's the same charge. It's going to be right in between them, isn't it? If I have a plus Q here and I have a negative Q here, if we draw a line in between them, the 0 point is going to be directly in between, right? Think of it like as, remember, topographic maps? This is a mountain, this is a valley, and to go from a mountain to a valley, you have to cross what? Sea level, right? A plain, a flat spot, right? Okay, so the voltage at infinity is 0. Infinity in electrical sense sometimes is the ground, and so the voltage at ground is also 0, right? But we can also talk about comparing the voltage at 2 points in space. I could have a voltage right here and then a voltage right here, right? And how would I figure out the voltage between them? Well, it would just be one minus the other, right? Because they're both referenced to infinity, I can reference them to each other, right? So I can find voltage differences in space, on objects, all that kind of thing. But the bottom line is, voltage of a point charge formula, pretty straightforward, isn't it? Doesn't even have a squared in the bottom. Okay. The shoe's got to drop somehow, right? So let's charge ahead. Let's find the voltage because there's a line of charge. Now, this is going to hopefully feel familiar, if not a little bit stress-inducing. Okay. So if I stick my line of charge on my x-axis here, and I say, well, I want to find the voltage right here at that point on my y-axis. Well, what am I doing? I'm finding the voltage. How am I going to find it? What am I going to break my line up into? Bunch of little voltages. That is not a d volume this time. I'm sorry, we just don't have a different symbol for voltage, right? Okay. So that's a little pieces of voltage, and those little pieces of voltage are going to be little tiny bits of charge, right? Point charges all along. So in a like manner, I have to come in here. I have to decide which point charge I'm going to use. Because there's a distance in here, I do need to know how far away this point is. Okay, well, if we're a distance y up the y-axis, and we're some distance along the rod, x, what is the distance from my point on my rod to the point on the y-axis? Square k dq over square root of x squared plus y squared, right? And now, what's my dq? Hint, you should already know the answer. Lambda dx. Remember all that? Okay, that's still the same. Goes in there. And now I can go ahead and write down this integral in its full glory. K lambda dx all over the square root of x squared plus y squared. And now I've got to do an integral, right? What am I integrating? Where are my limits? Where does it start? 0. And where does it end? Whatever length of thing I've got, right? All right. What's a constant in this integral? Y is a constant, but so is k and lambda. The dx stays on top. Square root of x squared plus y squared. Okay. I went ahead and looked up what the integral of dx over square root of x squared plus y squared is. It should probably come as no surprise. Like I think you can do this one by U sub. This ends up as a natural log. This ends up as k lambda times the natural log of x plus the square root of x squared plus y squared. And why is it no surprise that this comes as a natural log? It's 1 over, right, this xy thing with a lot of stuff along the way. So when I do that, right, when I evaluate all my limits and things, I get k lambda natural log of L plus the square root of L squared plus y squared. This is inside the natural log all over y. There we go. So there it is. For this particular setup, right, I have the voltage at that point, right, for a rod laying down on the x-axis along the y-axis. All right. Any like huge revelations or difficulties here? Like, let's not worry about why it's a natural log. That's just a math thing, right? But in terms of the setup, we've been here before, right? We've done it with charges. We've done it with electric fields. Now we're doing it with potentials. Yeah. When you put in 0, you got the natural log of 0, which is 1. And then you've got the square root of 0 plus L squared, which ends up being L. And why is it Y? I just confused myself. Oh, yeah. Square root of L squared plus Y squared is on the top. That's when I put the L in. When I put all the zeros in, yeah, I get the square root of Y squared, which is Y. Just answer my own question again. Symbols. All right. Let's do a ring. You guys don't need me anymore, right? No, you can do this.
No, please don't leave.
It's going to get worse. All right. So a point along the axis. We've got a charge on this ring. Let's say that the ring has a radius of a, and we are distance x. So this is the same setup that we had before. I'm going to pick a point here at the top so that I need to know the distance right there. What's the distance between that point at the top and point P? A squared plus x, the other way around, x squared. People get upset when I do that backwards, even though it's the same thing. All right, there we go. Now, could you write an R vector and find its length? Sure, right? But there's no vectors, so why bother? All right, so my potential is going to be adding up all the little dVs, which are a bunch of little dQs, point charges, using the point charge formula again. This is the integral of k dq all over the square root of x squared plus a squared. And if I stare at that for a little bit, I realize square root of x squared plus a squared. Where does that go? I know I haven't done dq yet. That's OK.
That's a constant.
It's a constant, right? The distance from point P, no matter where I am on that ring, stays the same, doesn't it? And k being a constant, means that it comes out too. We did the similar trick with the electric field, and all I'm left with is dq. And so I don't have to break down dq. If I integrate, if I take a bunch of charge and I cut it up into little pieces, and then I add all the little pieces up, what do I get? The charge. So the voltage of a ring at point P on its central axis is just going to be kq all over the square root of x squared plus a squared. And again, I know some of you are sitting there like lost. You go, oh, I don't remember any of this stuff. And then there's several of you that are going, why are we doing this? Like seriously, why? Why? We did it with charge. We did it with electric field. Why are we having to do it again? I'm going to show you why we do everything in voltage. I promise. You just have to kind of hold on for just a little bit. Okay? Let's lay out all of these things, and then I'll show you how we're going to find the electric field of a ring directly from this result. It's going to be cool. It's going to be cool. It's going to be like magic. It's going to be a little magic trick. All right. Let's take a break from doing integrals and do some more quiz stuff. Concept of the potential. All right, let's do a disk. Once again, we've been here before. Does anybody want to take a guess how we're going to find the potential of a disk? Break it up into what? Rings, right? We just found the ring equation. Since we know the equation for a ring, we'll just figure out how to get the integral to, right, put all those rings together. Again, we've done this before. It's just now, there's a whole lot less vectors in it. You're like, Mr. Balogh, why didn't you show us the easy part before? Well, back then you wouldn't have thought this was easy. It would have blown your brain just as much. Okay, so we're gonna do it in rings like this, right? And we're gonna have this. Well, what happened? Come back. We're gonna have a dr right down in here. Like we're gonna coming out. So we're gonna have and we're gonna have a point right here, and we've got to know like so. So is this distance right here, is this going to change now as we integrate? Yeah. Okay, because we're going to go, and in this time I'm doing r as the radius, right, that we're at. I'm trying things really small in there, I'm sorry. Yeah, it doesn't zoom in for you guys. All right, so same setup that we had last time. Voltage. Integral of all the little voltage pieces. The little voltage pieces this time are going to be the little tiny pieces of the ring formula that we had. We had a squared before, but I'm going to substitute in r here. And as far as our dq is concerned, what kind of thing are we talking about now? Line, surface, volume. This is surface. So sigma is going to be equal to dq over my dA, which means my dq is sigma dA. And it looks like I am taking a ring, 2 pi r, and then multiplying by a bump out in that radius to get a surface, to get a strip, right, around in there. All right, so now I can put all my pieces together. Integral of dv, which is k, and dq, which is 2 pi r dr, all over the square root of x squared plus a squared. Integrated from 0 to the big R of the disk, right? It goes all the way out to R. Oh boy. Setup done. Integral happening. R squared. R squared. They're all the same to me. R squared. Thank you. Yeah, because the integral would have been really easy at that point. All right. Let's go back to that. Can't do that. Okay. R dr all over the square root of x squared plus r squared. The integral of that thing can be solved by a u sub. At least that's what my notes say. If I let that be my u, then my du becomes 2r dr. And I can do all the u sub stuff, put all that in, and what I get, I'm going fast here. 2k sigma pi, this is the end result. Square root of capital R squared plus x squared minus x, right? Because we evaluate from 0 to r. The u sub here, we got u to the negative 1/2, so it becomes u to the 1/2 when you integrate, right? What?
Maybe I forget. What the sigma dA, how did that, is that just something? It probably is.
Did I drop a sigma? I dropped a sigma. I got too excited in my intermediate steps. Sigma there. Where's the other one I left? Sigma there. Yeah. Is that what you were worried about? Yeah. Okay. Yeah, no, I managed to drop the sigma, didn't check the units of my integram because I was worried about the u sub and got ahead of myself. All right. So there's the disk. Okay. The reason I've been trucking through this, okay, is because I wanted to get to what I think is the more powerful statement or procedure. And that is, how do we get back to the electric field from this? Have I made the case that integrating voltages is easier? Okay, it's easier for the obvious reason that you've seen this several times before, right? So your brain's kind of used to it. But why is it easier? No vectors, right? Okay, it's just like straight up, what's the distance? Integrate, right? So the setup is easier. There's less things to keep track of. I don't have to worry about like, well, what is my x vector canceling? Is my y direction doing something, right? There's none of that stuff in there, right? So hopefully I made the case that finding voltage is easier mathematically. When it comes to measurement, how many of you have had an opportunity to like measure voltages in a class or anything like that? Some of us, okay? So for those of you that have had a chance to do anything with electricity or use a multimeter or something like that, it's called a voltmeter for a reason, okay? Because it measures voltage. While these exist, there really isn't an electric field-o-meter. You don't take your probes out and go, what's the electric field? Okay? Because the electric field is really hard to measure. It's a pattern of forces, right? That exists because charges are around. But the thing that is easy to measure, the thing that you can always reference to infinitely far away, is electric potential, is the voltage. We've got devices that directly measure the potential of things, and they're called voltmeters, or multimeters if they measure more than one thing besides voltage. So in a practical sense, measuring voltages is very easy. We've developed the circuits to do that. If you ever come across a device that says it's an electric field-o-meter, it's really a voltmeter that's doing extra math for you. And I'm about to show you the extra math, okay? How do you get from the measurement of a voltage to an electric field? How do you turn a scalar into a vector? Here's the answer. So we're going to back up a little bit and go back to the original like integral definition I kind of dropped on you last Tuesday, a couple days ago, and I kind of skipped over it really quick. I was like, hey, you don't need to worry about this. Well, it's back. That original integral sort of definition of the potential. If we have an electric field, let's say we got an electric field that's, I don't know, doing this. Okay? And I want to know what the difference in potential, say, between 2 points in that field is. Then what I have to do is I have to integrate, like I've got to go from 1 to 2, okay? And figure out at every point along that dotted line what the dot product is between my electric field vector and the direction I'm integrating. Okay, which is painful. I'll give you that. So this isn't necessarily something that we want to do, right? We're going to reverse engineer this. We're going to measure the difference between 1 and 2 and see if we can't get the electric field back out. And so the way we're going to do that is we're going to concentrate on what's sitting right here. What's sitting right there? Well, okay, as you read, that's good. Okay, but back up a little bit.
Almost looks like flux.
Don't go there.
No, I'm not.
What's sitting on the other side of that integral symbol? What is dV? No. It's the little tiny piece of potential, right, that we are going to integrate over, isn't it? So in this definition of what voltage is, having this integral, I can look at this and go, oh, well, if that's the definition of electric potential, then I can kind of extract some information out of what that integrand is. It's a little tiny contribution to the electric potential along this path, this line that I'm integrating along. And it needs to be minus E dot dl, doesn't it? And I'm just reading right off the integral that my little piece of potential happens to be the electric field dotted into a little tiny piece of length. So generally speaking, being as inclusive as possible and taking in every possibility, at least in Cartesian coordinates, my electric field could be written as the magnitude of the electric field in the x direction times I hat plus the component of the electric field in the y direction times j hat plus the component of the electric field in the z direction times k hat. Have I done anything weird here? What did I just write down? I just wrote down a vector. I just wrote down the electric field vector in Cartesian coordinates, right? That's all I did. No mysteries, nothing. It's just could be in general what it is. Again, in Cartesian. Could I do this for spherical coordinates? Cylindrical coordinates? Polar coordinate? Yes, I could do it. We were just going to stick to Cartesian. Okay. In a similar way, I can write down what the dl vector is. Because it is a vector, right? We're dotting two vectors together to get a scalar. That's going to be, well, you want to take a stab in the dark as to what the x component of the dl vector happens to be? Don't think about it too hard. dx. It's dx I hat. Component magnitude times direction. Okay. Guess what the y component of the dl vector is? dy. And the z? dz. Again, getting the most general form of that vector I possibly can. And it kind of looks like we are on a collision course to having to do a triple integral. We have dx, dy, dz, right? Nope. We're going to get into something better. Some of you know where this is going, depending on which math class you've had already. Those of you that don't worry, you're not required to know. So what's dv going to be? What is this line now that I can go ahead and write this dot product? What's it going to be? There's going to be a minus. And then I've got a dot. These two three-dimensional vectors together. Do I panic? No. Because for every term that has mixed directions, say I and j, or j and k, or k and I, what's the dot product between two perpendicular vectors? It's 0. So what are the only terms in this multiplication that will survive? I's and I's, J's and J's, K's and K's, right? That's the only thing. And so what are the two terms that have I hats in them? Ex dx, right? So this will be minus Ex dx plus, what's the y term going to end up being? EY dy plus EZ dz. Again, I'm dot prodding these two together, right? I dot I is equal to 1, but I dot j or I dot k is equal to 0, isn't it? So even though I should get like 9 terms out of multiplying these two big things together, every term that doesn't have the same direction in it becomes a 0. And the only things that survive are the multiplications that have the same direction. That's just properties of the dot product and vectors. You can do it longhand if you want. I got rid of all the zeros. Okay? So, we're going to do another trick here. Little mathematical trick. We can now pick off the individual components of the electric field. In other words, Ex dx is independent of Ey dy is independent of Ez dz. You add them all up and you're equal to this dv, right? So I can say, look, Ex is going to be equal to negative dv dx.
Because they're doing their own integral.
And Ey, what will it be? dv over dy, and Ez. And you're like, wait, what about the adding? Well, if we add all of these up, we will get to dv, right? dv is the sum of all these things, but each individual thing is its own thing. And is the x component of the electric field going to change in y? No! Right? The x component only cares about x. It doesn't care about what's going on in y. Y hates x. Oh, no, let's not go there. Right? These directions are independent of each other, right? Especially in the dot product, because we pull off anything that doesn't behave well, right? And so this is perfectly legit. And what's more, these derivatives are I use the D word. I did.
Differential?
I did. Clean up your language. It's a derivative? Now, those of you who have me long enough will know that I start raging against derivatives, right? Because a derivative is nothing more than a what? It's a ratio. That's all it is, right? It's a change in one thing divided by a change in another.
Oh, it's just divided by dl.
But is this a derivative? If I take the derivative with respect to x of my electric potential, what will I get? I'll get the component of the electric field in the x direction. And if I take the derivative of the electric potential, a scalar thing, with respect to y, then what will I get? Y. I'll get the component of the electric field in the y direction. And if I take it with respect to z, what will I get? I told you it was like magic, right? So I can find the magnitudes of the electric field components in their specific directions, and I automatically know what direction the x1 is pointing. Right? Same thing for the y, same thing for the z. So, what we're going to do is we are going to write these derivatives a funny way. We're going to use a new symbol. In other words, the electric field vector is going to be, negative signs along for the ride, I hat dv dx, where I have been very careful. This is me not being sloppy. This is me using a new symbol that some of you may not have encountered yet. Plus j hat dv dy with kind of a funny curly script d, plus k hat dv dz. What is this funny curly d? It's a partial derivative. Where do you guys learn about these? Is this Math 6? Which some of you have starting now, like, because there's no Math 6 isn't required, right? Okay. So let's just, I know some of you haven't seen this yet, okay? So standard derivative d dx, right? Written with a standard d. Partial derivative is like this curly, I don't know how to describe it. It's like a script d, right? Okay. And when I get really sloppy, my d's and my d's look the same. A partial derivative is my favorite kind. A partial derivative is really how nature works. The vast majority of interactions that happen in nature do this instead of this. Let's talk about this for just a second. Your ddx's, the standard ones you came out of calculus. Do you remember the chain rule? That's what calculators are for. That's a good answer, okay? Because nature doesn't really do the chain rule. Why do you have to do the chain rule? What was the whole chain rule thing about? What if the independent variable or dependent variable, whatever the mathematicians talk about, right? But what if y did depend on x, right? What if they were coupled together? I'm not saying that there isn't coupled systems. There are. But a vast majority of systems that we look at in nature, they can do one thing in x and another thing in y, and they don't, one doesn't really affect the other. Okay? A partial derivative means you don't have to worry about the chain rule, right? A partial derivative means that anything that, like a partial derivative with respect to x, if your function is x squared plus y squared, what's the partial derivative with respect to x? 2x. What happened to the y? It's gone, because anything that isn't specified in the partial derivative is treated as a constant. All that stuff, all that partial, all that chain rule baloney about, well, what happens if the function dependent? Kick it out. Okay? So that's why we write that funny symbol, because in this particular case, the directions are independent of each other. We're going to get a scalar back anyway. They don't care. And so all that matters is your derivative with respect to the direction that you're taking the derivative of. There is a shorthand notation for this. The shorthand notation is that the electric field vector is equal to negative, and then we're going to use the delta, but upside down. Upside down delta, vector sign over the top, dotted with v. That upside down delta is an operator, the del operator, that's exactly right, which by definition, the del operator is the partial derivatives of the directions with their corresponding derivatives. Okay, there we go. Okay, so del f, I kind of did that a little bit wrong. Del f is equal to, right, that times my function. So this notation right here, okay, this is a vector calculus type of notation, right, where in this del we have scrunched this idea, right, of partial derivatives and the directions multiplied together, being able to pick off, okay, all these different kinds of things. And in your Math 6 class, they probably started going off about gradient at this point, okay? Well, you probably learned gradient in terms of like the vector that tells you the direction that the slope is pointing. Like if you've got a two-dimensional surface, right, and the gradient can tell you whether the surface is going up or down or something like that. That's exactly what electric potential is. It's a surface that tells you what the electric field is doing. If you can find the gradient of your potential, what do you now know? What your electric field is doing. You know the topology, you know the topographic map, electrically speaking, for what's going on. You can figure out what the electric fields are going to do. So I'm going to demonstrate this on how to get back to electric field. Just a real quick aside, this was Cartesian coordinates. In polar coordinates, you can get the radial component of the electric field. You want to take a guess? D, well, it's going to be dV, dr. This is the radial component, not the theta component, okay? In what direction? Good, r hat. Okay? The only reason we show you the radial component is because it's the only component we're going to concern ourselves with in Physics 4b. There are other components in the really it's cylindrical or spherical. We don't use polar coordinates in 3 dimensions. But so when you get into the weeds about these differentials, right, pulling them out, well, in spherical coordinates, it's theta and phi, right? The two angles that reference where you are around and from the North Pole of a sphere. Those get really messy. Like it's like 1 over r squared sine phi d theta, something. You pick up a lot of extra baggage along the way. Did they teach you that in Math 6? They don't do that? It's too bad. Because it gets really hairy, really fun, really fast. And by fun, I mean fun spelled M-A-T-H. Okay, so let me give you an example of finding the electric field from the potential. Then let's use the electric field of, let's see, which one did I pick? I picked the ring, okay? So let's go back to the ring. What was the ring? The ring was V of a ring we found today was KQ over the square root of x squared plus a squared, right? We use that to go find the disk. Great. We want to find the electric field of a ring, though. So let's say we have a ring of wire, right? Loop of wire in a ring. It's got charge on it, so it means it's going to have potential. We're on the axis. We found out what the voltage is, right? We're sitting here on our ring. We're at point P. We found the voltage. Now we want to find the electric field at that point. Our choices are go back into integration hell or use our new tool. That one right there, right? Okay. Let's take advantage of some symmetry. Why not? What do we know about the electric field at point P? It's going to go like that. It's going to go like that. So what's going to happen to the y components? They're going to cancel out, right? So that means that all that's going to survive are what? Just the x components, right? So we go ahead and we say, well, only x survives by symmetry. Whoa. And so now that means that our electric field is going to be minus dV dx only, right? That's just going to be I'm just kind of peeling off the x component, right? So now I have to take the derivative with respect to x only of kq x squared plus a squared to the negative 1/2, right? Okay. Well, what is that? I missed a minus sign. I dropped a minus sign. K doesn't matter. Q doesn't matter, right? Negative KQ. Derivative of this thing with respect to x. Okay, can you take derivatives of this thing with respect to x? Yes. The answer is yes. What do we do? So has it been that long? We take the derivative. So this is something raised to the 1/2, right? What is that? So what do you do? What's x to the negative 1/2? Derivative of x to the negative 1/2. It's x to the negative 3/2. Derivative. What is the derivative of x to the negative 1/2? What do you do? This doesn't have to leave this room. It's okay. It's okay. Okay. You bring, what do? Bring the and then the Are we good? Times the derivative of the stuff that was inside, right? Okay? All right. Using this pattern, what's the derivative of x squared plus a squared to the negative 1/2? Negative half comes down. Thing stays here. Negative 3/2 now times 2. Oh, okay, we got there in the end. Holy cow. And then we don't have to worry about a squared because it's a constant. Even if it was a y or a z, it would still be a constant because we're using partial derivatives. There's no chain rule. Yay. Whew. This is what doing lots of integrals does to people. Right? Destroys derivatives, doesn't it? All right. There's negatives in here. As a matter of fact, there's 2 negatives. What happens to 2 negatives? Becomes positive. I've got a KQ. The 2's cancel, don't they? Leaving me with an x, right? All over x squared plus a squared to the 3/2. And because this is EX, right? We now know that. So E is this thing, all of that times an I hat. Do I need to pull out the notes from chapter 22 to prove to you that this is exactly the same thing that we got? Yeah, let's just pretend that chapter never happened. Lewis, you're killing me. All right. Yes, we found. All right.
We should all get 20 extra points.
Yeah, we did the electric field, and that's what we got, right? This is exactly what we got. Even the direction was right. It's positive along the axis, right? Did we have to double? Did we have to go, oh my gosh, and 2 times? No. We didn't have to do that either. It's like it knew. Why didn't I show you this first? What would have happened on day 2 in this class if I would have dropped the gradient on you? Yeah, I mean, right? Okay, it's bad enough giving you a bunch of integrals, but at least you're kind of like, oh, Mr. Balogh, I can do an integral. I'm awesome. Well, I know you can do it. Can you set it up? Oh. Doesn't it?
Yeah.
Say that again, Rose. Say it out loud.
This makes way more sense than the integrals.
Isn't this better?
Wait, then why did we do the integrals earlier?
Right? Right? It calls into question everything that we do, right? Why did we do the integrals earlier? You kind of have to understand where it's coming from, right? The electric field is what it's all about. However, when it comes to the day-to-day, like actually working with wires that have charges in them, what are we going to measure? Voltage. We can figure out what the electric field is doing, and so therefore predict like what the antenna is going to do, or how not to shut down the pacemaker, or whatever the case may be. We can figure all that out. But what we're going to measure is voltage, right? It's a powerful, powerful abstraction. It's kind of like all that we've been doing since the beginning of the semester. We started with Coulomb's law, which rules everything. And we said, okay, you know what, Coulomb's law, let's talk about electric field instead. And you're kind of like, field, whatever, okay. And then now we've moved to voltage, which is like, we're just getting further and further from the actual thing. Well, why do we do that? Why don't we just do everything in terms of Coulomb's law? Why don't we just talk about the force of the charge coming from the plug? Why do we talk about voltage? It's easier. It's easier mathematically, right? It's easier sometimes like conceptually. This is where we are about to go, okay? This is the inflection point. We're going to go from to Because the math, all of a sudden, we're going to be like, the hard thing's going to be dividing. You okay over there, Lewis? Yeah, a little. Yeah, it's speechless. What? Was leading to this moment.
Are the same as what we're doing now?
Yeah.
This is just shorter?
Yeah.
So I could have did, okay.
You feeling ripped off? I don't tell the teacher that. It's fair. You can feel ripped off. We did the same thing to you in 4A. Do you remember what it was? What? Yeah, conservation of energy. Right? All of a sudden, we were able to do problems that, like with Newton's second law and projectile motion, would have taken forever. Did them in like 4 lines with conservation of energy. And some people were mad. They're like, why didn't you start here? And I'm like, well, the reason this sounds easy is because we started, right? There are some places that teach physics that start with conservation of energy, and guess how screwed up they are? Pretty bad, right? So like, pick your poison. All right, let's talk about what happens when you've got voltages and conductors. So, what's the voltage? No, let's back up. Here's a lump of metal, okay? We already know what the electric field is inside of a conductor. What is it? 0, right? We had to go through Gauss's law to figure all that out, right? Okay. What is the potential of a conductor that has charge on it? In other words, if I dump charge on this lump of metal, where does it go? It goes to the outside. We know all of this, right? Fundamentals of Coulomb's law, Gauss's law helps us figure it out. And we learn that the electric field inside is going to be 0, right? So if I take any 2 points in or on the surface of this conductor, so inside the bulk or anywhere along the outside surface, doesn't matter. I can take point here, or I can take a point here and a point here. And I figure out what the difference in voltage is between those points. What am I going to get? Inside, it's really easy to see. If the electric field in there is 0, what are you going to get as the voltage of those 2 points? 0. And what's 0 minus 0? 0. All right, let's do the surface of the conductor where the electric field is not 0, right? There's charge there, isn't there? How much charge? Same amount at one point as it is on the other. So what's the difference? If the magnitudes of the voltage are the same on both of those points, and I'm taking the difference, It doesn't matter what the number is. What's the difference in potential? 0. You are looking at the reason why birdies can land on power lines and not die. When a bird lands on a power line, why aren't they immediately barbecued? Their feet aren't conductors, but at 20,000 volts, they certainly could be. What's the difference in electric potential across their feet? It's 0 because one foot's at 20,000, the other foot's at 20,000, and what's the difference? 0. So no electric field, no flow of charge, no nothing's going on. No forces. Okay? Okay. So little birdies are okay, but big birdies are not. My grandfather was he was an industrial chemist for half of his life, and the other half of his life he was a farmer. And he had a big farm out in New Mexico, and unfortunately, large birds of prey like owls and hawks and once an eagle had died underneath one of the power poles on the farm. Okay? Why were the large birds of prey dying from the electrical shocks and the little birds weren't? If an owl comes in for a landing, birds typically do like a flare, right? They catch a big scoop of air to slow down so they can plop down on the wire. So if you come in and you do that with respect to the wire so that your wings and your legs are all at the same voltage, then the difference in voltage across the owl is 0 and nothing's happening, right? But if the owl were to come in and land, usually on like the tower, the pole, and it put its wings across the phases, meaning positive 20,000 over here and negative 20,000 over here, now what's the voltage difference? 40,000 volts, right? And so we would go pick up the dead carcass and so the bigger the bird, the more chance there is for them to reach across the phases, right? The little birds would never have the wingspan to do that, right? But the big birds did. This is why if there's ever an accident on a high voltage power line that PG&E is working on, that they do not immediately go rescue that lineman. If a lineman is dangling from a 500,000 volt line, like the big ones you see over there by 99 and on the West Valley over by 5, right? Those are 500 and I think 700,000 volt lines now. Linemen's working on the lines and they fall, you don't rush up and grab them. Why not? Because they're at 500,000 volts. And what's the ground at? 0. And so you have to use special rescue techniques, right? Okay, to pull that off. Now, this is not one of those rescue techniques. But I do want to show you something equally crazy. How do you fix a power line that's at 500,000 volts without shutting it off? Because you've shut off one of these, you've shut off the entire town's supply of electricity.
Then in the 1980s, helicopters and barehanded
I'm gonna turn off the
combined for a
audio.
remarkable new way to maintain live lines.
It doesn't really work.
With this technique, the
Okay,
lineman and the
helicopter.
helicopter are both
Notice,
energized to the line voltage.
Lineman's got a pokey in his hand.
And again, they are
Okay.
safe because they are
What's
not
he
touching
doing?
the path to the ground.
Charging up the helicopter to what?
Helicopter line crews can work much
Same
faster
voltage
than
as the
traditional
power line.
teams on extremely high voltage transmission lines.
This is
Linemen
nuts.
equipped with bucket trucks and hot sticks can
What?
replace about 8 line spacers in a day.
It's dangerous.
During the
Look
same
at this.
time,
You got a
skilled
helicopter
helicopter team of
hovering
line
next to you got 2
can replace over
helicopters
200.
hovering next to a 500,000 volt line.
In my career, I would never dream
Well,
that I
yeah,
would see
I
a
know.
helicopter doing power line work.
But it's still
I would think it's a little
dangerous.
scary the first time you do it too. You're sitting there
Yeah,
on
he
the
did- he
platform on the
talk
side of a
about
helicopter and
how
you fly
crazy this
right
is.
next to a
Look
wire.
at this guy.
Yeah, you're hoping that the propellers don't get tangled up in anything.
And of course women
And
can
some
do
of
this
these
too. I
pilots,
know
I
I'm
have to
saying it from
commend
the
them. They
male
can
point of view. But
hold
like,
a helicopter in the same place as long as
notice,
it's anything I've ever
notice
observed.
what happened. What did the, what? As
These guys
the
are extremely
helicopter
good at what
goes
they do,
away,
and I commend them.
what is the lineman making sure to do?
They do a good job. They're safe. About
The
the only time they
helicopter
ever
has
have
to
anything happen
move
is when
away.
they
Now,
have equipment failure.
helicopter blades, as they beat through the air, build up static
Line maintenance
electricity.
with
So they end up with their
helicopters is
own
expensive,
potential.
and there have been
Different
fatalities.
from the
But today,
power
linemen
lines
and
potential.
pilots train for
And
2
as they
years to
approach,
master
what do
the
they have to
technique,
make sure that
which
they
is
do?
considered safe under the right
Equalize
conditions.
the potentials. Why do you want to equalize the
However,
potentials?
no safety tools, procedures,
So that
or
there is no
regulations
flow
are
of
effective
electrical
if a
charge,
lineman loses
right?
his focus
Now,
and concentration.
when linemen started doing this, okay? When linemen started, by the way, I got that clip from the History Channel before it went weird. When they first started doing this several decades ago, they started complaining of nausea, dizziness, disorientation, tunnel vision, not quite blacking out, but wanting to. These were people that were used to, so the typical way of doing this is in a bucket truck, where they park a truck underneath the line, they get in a bucket that's insulated from the ground, and they bring the bucket up, and they slowly bring the bucket up to 500,000 volts as they approach the line, right? Okay? And then so they're used to working at high altitudes, all that kind of stuff, right? It wasn't like a fear of heights that was getting to them. This was something new. And so they went back, scientists took a look at them, doctors took a look at them, saw that blood flow was being affected in their brains. From what? The electric field that existed around the wires, right? Did you notice what they were wearing?
The metal thing.
They were wearing a flight suit, but these were special flight suits. So they had helmets, right? But they also had the hood of that flight suit up over their helmet. They're wearing a Faraday cage. Because if you're inside, mostly inside of a metal mesh, what's the electric field inside? The electric fields around those power lines were causing blood flow disruptions in their brains and organs. By putting them inside of a Faraday cage, fix that problem. I will see you on Monday for the exam autopsy.